Hello, welcome to this 30-minute supplement on effective potential energy for non-rotating black hole orbits for the Gravitation and Black Holes course. The lecture script for all the supplemental videos is available at a link given in the description of this video. We will learn about the effective potential energy for a small mass, lowercase m, orbiting a non-rotating black hole of very large mass, capital M. Rotating black holes are more complicated, and we will not give those equations in this video or in this course. In supplementary video 5 on Newtonian orbits, we covered the Newtonian effective potential energy as a function of distance, lowercase r, and angular momentum, uppercase L. L is a parameter for this equation, but here I'm not showing L as an argument to the potential, nor as a subscript. Treat L as an implicit parameter. This needs a general relativity correction for black holes, neutron stars, and even for white dwarfs and the Sun for high accuracy. This is the effective potential energy using general relativity. It looks much different. It starts out with an mc squared term, rest mass energy. Then there's this second factor, square root of 1 minus Schwarzschild radius over r. We've seen the second factor general relativity correction term repeatedly in the main course, and we've certainly seen the Schwarzschild radius 2gm over c squared in the main course. This third term, square root of 1 plus L over mrc squared, is the angular momentum contribution. So the Newtonian expression is the sum of two terms. The general relativity expression is the product of three terms, although the first term does not involve r or L. The zero reference of energy has changed here. At infinite distance, the Newtonian effective potential energy tends to zero. Infinite r, the expression goes to zero. Whereas this general relativity effective potential, if r is very large, this goes to 0, we get square root of 1. If r is very large, this goes to 0, we get square root of 1. So the effective potential tends to the rest mass energy, mc squared. The rest mass energy, mc squared, is not included in the Newtonian expression, but we have the freedom to include any amount of energy as the zero reference. We just choose in the Newtonian case to be zero energy at infinity. But in the general relativity case, we always have to take the rest mass energy into account. This general relativity effective potential energy is the product of three terms, whereas the Newtonian effective potential energy is the sum of two terms. Let's see that the general relativity version reduces to the Newtonian version plus the rest mass energy when the distance is much larger than the Schwarzschild radius and the angular momentum is much smaller than the denominator, mrc. So for orbital velocities much smaller than the speed of light. So for those conditions, the quantity rs over r is small, and we can use a Taylor series expansion of the second factor, and this is the Taylor series expansion up to three terms. And if the angular momentum is small compared to the denominator, we can do a Taylor expansion of the third term to 3 terms, and we get this product, which at first glance does not look too helpful because now we have 9 things, but it is helpful. If we group them and we ignore the terms whose radial contribution is going to be 1 over r cubed and 1 over r to the 4th and so on, we get 4 terms inside the square brackets. We get 1 from 1 times 1. We get minus Schwarzschild radius over 2r from this times 1. We get 1/2 L over mRc squared from 1 times this. And we get minus 1/8 Schwarzschild radius over r squared from this times 1. All the other terms are higher order, and we are not interested in them in this lecture. Now we multiply the mc squared times each of the individual terms. We get mc squared. When we multiply mc squared times the Schwarzschild radius, remember the Schwarzschild radius is 2gm over c squared, so 2 cancels with 2. We get gm m in the numerator divided by r. When we multiply mc squared by here, this c squared cancels that c squared. This m cancels one of those m's. We get L squared over 2mr squared. And we get this for the 4th term. Now here was the Newtonian potential, but remember it did not include rest mass energy. If we take the Newtonian potential and we add in rest mass energy, the general relativity expression is approximately that, because for r much larger than the Schwarzschild radius, we can ignore this 4th term. So the general relativity version does reduce to the Newtonian version plus the rest mass energy when the radial distance is much larger than the Schwarzschild radius and the angular momentum is much less than mRc. That's good to know. But our interest in the remainder of this video is going to be close orbits of non-rotating black holes. So we need the full general relativity effective potential. So for the rest of the video, we're going to be using the full expression. This formula is valid outside the event horizon. Inside the event horizon, we would be trying to take the square root of a negative number. We're not going to do that. And so for the radius outside the event horizon, this number is less than 1. 1 minus that is going to be between 0 and 1. The square root is going to be between 0 and 1. As we approach the event horizon, r approaching r sub s, this expression is going to approach 0. And the effective potential energy approaches 0. And this is going to be regardless of the rest mass energy. This is called the pit. In this graph, the horizontal axis is r divided by the Schwarzschild radius, going from 0 to 15. The horizontal axis is effective potential energy divided by mc squared. So 1 here is mc squared. The red curve is the general relativity curve, and as we get closer to the Schwarzschild radius here is shown as the solid black vertical line. As the radius gets closer to the Schwarzschild radius, closer to the event horizon, we get the pit, where the energy plunges to zero. We will learn shortly that there is a minimum value for the angular momentum for circular orbits. This graph is the curve for 1.2 times the minimum angular momentum. The red dashed curve is the Newtonian effective potential energy plus 1 for the rest mass energy. So that curve would continue going to infinity as we get closer and closer to the origin. But that's Newtonian, and this is a black hole, so we don't expect that to be a correct description near a black hole. The solid red line is the effective potential energy for this non-rotating black hole for this particular value of angular momentum, 1.2 times the minimum. Far to the right, far from the gravitating object, the Newtonian and general relativity curves converge to one another, and they approach the rest mass energy, which is the horizontal black line. The black dot shows the minimum of the Newtonian curve, which is the radius and energy of the circular orbit for this angular momentum. The green dot shows the local minimum of the general relativity curve, which is the radius and energy of the stable circular orbit for this angular momentum. Notice that general relativity has pulled the Newtonian circular orbit, the black dot, to a closer radius and more negative, more bound energy, the green dot. This is a much larger effect near this black hole than for Mercury orbiting the Sun that we mentioned in supplementary video 5 on Newtonian orbits. The red dashed Newtonian curve increases to infinity as it approaches the origin. In contrast, the general relativity curve turns down, has a local maximum, and then crashes toward zero energy at the event horizon, the pit. Every angular momentum for which there is a circular orbit has this pit. The red dot here shows the local maximum of the general relativity curve, which is the radius and energy of the unstable circular orbit for this angular momentum. An object can orbit at this radius, but if it is perturbed inward and does not counter with some thrust, it will spiral into the event horizon. If it is perturbed outward and does not counter with some thrust, it will spiral outward. Let's expand the diagram to look at energies near the black horizontal line, the rest mass energy mc squared. So we're not looking all the way down towards zero anymore. We're looking in the region of 1. The energy at the green dot stable circular orbit is 0.966 mc squared. To achieve this orbit, starting initially at rest, far from the object, we would have to lose 3.4% of our initial rest mass energy. That is to say, this amount of energy, from rest mass energy mc squared at infinity to the circular orbit, we would have to lose 3.4% of our initial mass energy. This seems impractical to achieve even with a science fiction antimatter drive. But maybe there's some advanced civilizations that have figured it out. This is also the amount of energy radiated as light and X-rays by accretion disk particles orbiting the non-rotating black hole before they spiral into the event horizon. The radiated energy is much higher for rotating black holes, which we're not covering in this supplement. The energy at the red dot unstable circular orbit is 1.02 mc squared. To achieve this orbit starting initially at rest at infinity, we would have to increase our energy by 2% of our initial mass energy. Suppose we had a non-circular orbit with slightly higher energy than the green dot. Suppose we had a non-circular orbit with slightly higher energy than the green dot, which I'm showing as this blue horizontal line. It should be perfectly horizontal. I didn't draw it perfectly. This orbit will have a minimum and maximum distance, minimum, maximum, turning points, but will deviate from the ideal elliptical orbit of Newtonian mechanics. Far from the gravitating mass, the deviation would start with precession of the point of closest approach of the ellipse, but here, so close to the gravitating mass, a black hole, the orbit will precess so fast that it's not an elliptical orbit. I don't have an image of such an orbit, but imagine some spirograph pattern if you know what that is. As we covered in the main course, here is the angular momentum for circular orbits, whose radius must be larger than 1.5 Schwarzschild radius. We get this relation by taking the partial derivative of the general relativity U effective expression with respect to r, setting that to 0 and solving for angular momentum. We can rewrite this as this expression absolute value of angular momentum over Schwarzschild radius mc equals this expression on the right. We're only going to use radii more than 1.5 Schwarzschild radius, so this denominator is going to stay positive, but it will get close to 0 as r gets close to the Schwarzschild radius. Let's graph that. The red curve is the curve of angular momentum. The horizontal axis here is r divided by the Schwarzschild radius. The vertical axis is magnitude of angular momentum divided by the Schwarzschild radius mc. There is a minimum value for the general relativity curve here for circular orbits, unlike the Newtonian result. You can have a Newtonian result. There's a minimum when you get to the surface of the object. For the black hole, that surface, there is no surface. There's only the Schwarzschild radius. The minimum angular momentum for a circular orbit is this value. L min equals square root of 3 Schwarzschild radius times mass times the speed of light. Mercury's orbit around the Sun has about 1,800 times the minimum general relativity angular momentum for the Sun's mass. Let's rewrite the effective potential energy in terms of L divided by L min. Now, let's graph that for multiple values of L over L min. This graph again shows the effective potential energy curve, but now for 4 values of angular momentum. The minimum times 1 is the orange curve. Minimum times 1.1 is the purple curve. Times 1.2 is the red curve. Times 1.3 is the green curve. The orange graph is for the lowest value of angular momentum, L equals L min. The orange dot is not a minimum, it's an inflection point. It occurs at 3 times the Schwarzschild radius. This is the innermost stable circular orbit, or ISCO. Actually, this orbit is half stable. If the orbit is perturbed inward, the object will spiral into the event horizon. But any angular momentum larger than the minimum has a stable circular orbit. The dotted blue curve is not energy versus distance for a single angular momentum. It is the locus of all circular orbits for all angular momentum values. All circular orbits along the dotted blue curve to the right of the orange dot, here, 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 are stable circular orbits. All circular orbits along the dotted blue curve to the left of the orange dot, here, here, and here, are unstable circular orbits. It's not obvious here, but all unstable circular orbits have radii between 1.5 and 3 Schwarzschild radius. The dotted black vertical line is 1.5 Schwarzschild radius. No circular orbit is possible inside 1.5 Schwarzschild radius. Inside 1.5 Schwarzschild radius, all orbits spiral into the event horizon. As the unstable circular orbit radius approaches 1.5 Schwarzschild radius, the effective potential energy increases toward infinity. Now, because I'm interested in science fiction representations of black holes, we're going to switch to looking at time dilation for circular orbits. In the main course, we learned that the time dilation between a circularly orbiting observer orbiting a non-rotating black hole and a faraway observer increases strongly as we approach 1.5 Schwarzschild radius. As r approaches 1.5 Schwarzschild radius, this fraction gets closer and closer to 1. 1 minus it becomes closer and closer to 0, and the time dilation that the faraway observer sees approaches infinity. We also learned that a human observer in circular orbit, they could stand the tidal acceleration pretty close to 1.5 Schwarzschild radius for a supermassive black hole, but not for a stellar mass black hole. The innermost stable circular orbit for the non-rotating black hole is at 3 Schwarzschild radii here. And when we plug that in here, we get a time dilation of 1.4. That's not very exciting in terms of science fiction. If we want higher time dilations and we need a stable circular orbit, like for a planet, like for Miller's planet in the film Interstellar, the only way to get higher time dilations for a stable circular orbit is if the black hole is rotating rapidly, which we covered in the main course, but we're not going to cover the complicated effective potential energy curves for rotating black holes in this video or in this course. Now, in this graph, the horizontal axis is not distance anymore. The horizontal axis is time dilation from an unstable circular orbit to a faraway observer. And the vertical axis is energy of the unstable circular orbit. For non-rotating black holes, we can get higher time dilations for the unstable circular orbits, which are closer in than the stable circular orbits, and so we get higher time dilation values. Here's a graph of time dilations horizontally versus energy vertically for unstable circular orbits of the non-rotating black hole. So now we can just pick out a time dilation value we want, and we can see what the energy is for that orbit. Nice as you please. At twice the Schwarzschild radius, which has an angular momentum value of 1.155 Lmin, there's an unstable orbit with a time dilation factor of 2 here that does not require an energy boost or a reduction from the faraway rest mass energy. The energy value is 1. So it's at least in principle energetically easy for a spaceship that came initially at rest far away to enter this unstable orbit without a big energy correction, and we get a time dilation factor of 2. But a time dilation factor of 2 is not good enough for a science fiction portal to the future. We can get more time dilation here, more time dilation at closer in unstable circular orbits, as long as we can tolerate the tidal acceleration, which is pretty tolerable for a supermassive black hole. But our penalty is that these unstable orbits require substantial impractical energy boosts to get to that orbit, multiples of our rest mass energy. Impractical. Don't know how it can be done. Maybe some advanced civilization figures it out. So, if we really want to get high time dilation, we should choose a rapidly spinning supermassive black hole. But we're not going to cover their complicated effective potential energy in this course. To learn the formulas for rotating black holes, there is a free ebook that I'm going to recommend, and the URL is in the lecture script. though the ebook is pretty long, 650 pages, and it takes a good deal of work.